Good afternoon, Cal Poly committee members. My name is Ron Cibron. I'm applying to a position in your university. So, I'm going to give you a 10 minutes presentation on static friction. So, starting now. Walk into an empty classroom. Assume that it's full of students. This is a class in general physics, calculus based. And today we'll talk about static friction. Our plan for the week, ladies and gentlemen, is I'm going to have a health session tomorrow at 7 p.m. because we're going to have our first hour exam later this week, okay? Then on Wednesday we're going to have our first context-rich problem. You guys remember that these are the problems that I told you about, where they'll be as close as possible to a real-life situation. These were problems designed originally by Kenneth Heller of the University of Minnesota, and we'll have our own little version for some of this. Tuesday or Thursday, we'll have a lab on friction, and said our exam's gonna be on Friday. Questions? Yes, Dave? Now, I'm sorry, you cannot bring your laptop, you cannot bring your iPhone, you cannot bring a friend either. You need to learn some skills, and those skills will be applied then in your engineering field, and it's the easiest place to learn them here in physics. So that's why we insist that you start simple, okay? So later on you will find all the apps and everything else, but you need to get it here first, then you can put it there. Okay, today we're gonna cover Newton's 3 laws in some sense or another, and when we used Newton's 3 laws so far, free body diagrams and all that jazz, we use gravity, the force by which Earth is pulling on you, normal force or reaction force, which is a force that prevents me from accelerating towards the center of the Earth, tension, right? And today we're gonna do mystery force, yeah, friction, but for the time being it's mystery force. How do we know it's there, what it is, how we measure stuff, what are the equations, which you all love, but you'll find out that it's important to not quite stick to those right away. And let's start, okay? 3 demos, okay? As always, 3 demos, few demos, right? Piece of wood on metal, piece of wood on metal, piece of wood on metal. When I push on that piece of wood on metal, right? Push this way. First, when I push, really gently, does it move? No, but you're not pushing. Yes, I am. Prove it to me. Here we go. Remember that, fellas? That was our dual force range thingy, same as in a supermarket. Measures force in newtons, and you push just a little bit, and it reads. So that means there is a force there. Or if you pulled it, it reads, there is a force there. Here you push, doesn't move, but there is a force growing until you kind of break something and it starts moving, right? Same thing here. Let's assume there's no friction right here between these two surfaces, between the clamp and the wood, but between the big metal plate and the wood there is, and push nothing, then I can sort of move it, right? Got it? Same thing here. Raise it. Does it move? No. Are there no forces on it? There are. What's the net force on it? 0. There is gravity. There is normal force. But together they should have pushed it down. Must be something else. Yep. So, what is that something else? We said that looking from above here, or looking from there, we said there was, same thing, block of wood, metal, okay, clamped together, so something holds them together, okay, and there is a force acting this way. I'll call this force push, put a vector above it so that you know it's a force. Okay. You know it's a normal force, right? Because it's a contact force normal to the surface, right? And now I'm gonna do the free body diagram or force diagram. Obviously, you shrink the object in question, in this case the wood, into a point. Push is this way, right? There is some force that way, some force that way. In this case, force that way, that's gravity. Force that way is a normal force, but there has to be a force that opposes everything, and that's the force of friction that starts small, grows until it breaks. Okay, how do I know that there is really equal frictional force when I push it just a little bit? How do I know that there is an equal frictional force right there? Because it doesn't doesn't move. Use a physics term. Accelerate. Doesn't accelerate. Okay. Same thing here.